Guys, welcome to Send the Mix online tutorials. On today's episode, we'll be discussing on diodes and diodes application. Welcome back. A diode is a semiconductor. And what is a semiconductor? A semiconductor is a material that is neither a good conductor or a good insulator. Now, in the purest form, semiconductors have few applications in electronics. That is to say, in their purest form, semiconductors like silicon, gallium, antimony, and the rest, they have little applications in electronics. But the adding of impurities make them useful, and the adding of those impurities is what we call doping. As I said earlier, semiconductors have few applications in electronics. However, when the characteristics of a pure semiconductor are altered through a process of doping, it can be more useful in electronic devices. Now, the most basic semiconductor devices we have is the diode. We have the diode. Diode is the basic semiconductor device that we have. A device that allows current to pass through it in only one direction. A diode is a device that allows current to pass through it in just one direction. The symbol for a diode is this. It allows the passage of one directional current. That is to say, it's a unidirectional device. It allows a current to pass through it in only one direction. One of the applications of this diode is the conversion of AC voltage to DC voltage. Now, when the diode is used to convert AC voltage to DC voltage, we call it a diode rectifier, or we call it a rectifier, which is referred to as a rectifier diode. When it is used to convert from AC to DC voltage, we refer to it as a rectifier. So that is how the word rectifier is. If you check the dictionary, rectifier means to rectify, to amend, to make something work, to improve or develop something. So that is what rectifier is used in that term mean. Now let us talk a little bit on these semiconductors that we have been talking about. Now, semiconducting materials conduct less than metal conductors. However, semiconducting materials conduct less than metal conductors, and also conduct more than non-metallic conductors. They conduct more than insulators, but they conduct less than metal conductors. Semiconducting materials, as I said earlier on, as example of silicon, gallium, and carbon. Those are types of semiconducting materials. Among all, silicon is widely used among all these semiconducting materials I just mentioned. Among all, silicon is widely and mostly used in electronic application. So now we have two types of semiconducting materials. We have the intrinsic, and we have the extrinsic. We have the extrinsic conducting semiconducting material. I want to talk about the intrinsic. These ones are the semiconductors that are in their purest form. They are the ones in their purest form. While the extrinsic semiconductors are semiconductors with other atoms mixed with the main atom of this semiconducting material, or we can in other words say call extrinsic semiconductors as doped semiconductors, the ones that are doped. That is to say that an impurity atom has been added to the initial atom of the semiconducting material. So you can either say extrinsic semiconductors are the elder brother of an intrinsic semiconductors. So now the addition of these impurity atoms, as I said earlier on, is called doping. It's called doping. Doping alters the characteristics of the semiconductive conductivity. It alters the conductivity mainly. That's just when you dope a semiconductor. What are you expecting? You're expecting the semiconductivity to increase. Now, when the silicon crystal is doped with a pentavalent impurity atom, we have an N-type semiconductor. Let's say let us say silicon. Let's say silicon with its four valence electron is bonded, or will I say yes, is bonded covalently with any pentavalent impurity atom. That is to say, an atom that has 5 valence electron. When this silicon is bonded with it, we have an N-type semiconductor. When a semiconductor is bonded with an N-type, is bonded with a pentavalent atomic particle, we have an N-type semiconductor. But when a silicon crystal is doped with a trivalent atom, we have a P-type semiconductor. So with that being said, we've discussed now on P-type and N-type semiconductors. Now there is a phenomenon or a process where this P-type and this N-type semiconductors come together. When this P-type and N-type semiconductor come together, we have a PN junction diode. We have a PN junction diode. Now a diode is made by this is a diode. Now a diode is made by joining the P and the N-type semiconductor. Now let's say now this is a P. Let us say this is a P-type semiconductor. What describes a P-type semiconductor is that its major current carriers are holes. But for an N-type semiconductor, its major current carriers are free electrons. Let us say now this is a P-type semiconductor, and this is an N-type semiconductor. So now when they are joined, when you join them together, this is what happened. This is what happened subatomically now. So when you join them together, let's say this is the holes, and this is the free electrons. Now when you join them together, this is what happens. Now these holes pass through what I call a barrier potential. These holes pass through what we call barrier potential. Now for these holes now to jump over these, to jump from this P-type semiconductor to the N-type, to merge with it passes through a barrier potential. For silicon, the barrier potential is 0.7 electron volts, and for germanium, the barrier potential is 0.3 electron volts. So now when it passes through this, when it comes here, then what happens? Then you have a region. We call this depletion region or depletion layer. We then have a depletion region here. We have a depletion region. Now what happens in the depletion? What happened in the depletion region is that these holes join with these free electrons at this point. Now when these holes keep on coming into this, free electrons, it gets to a point where it stops. Coming. What stops it at that point is the barrier potential. That the barrier potential stops it from migrating from the P-type semiconductor to the N-type semiconductor. So now the region at which they have now merged together, the region at which they have now come together is what we call the depletion region. So now this is the holes and this is the electron. Now you can have the plus here, you can have the minus here, the plus here, the plus here, the plus here, the minus here, the minus here. It intertwines. Now they come together. So now when they come together, in this way, you now have a diode. You now have a diode. So now there's also a type of PN junction diode. We have the forward biased PN junction diode. This is a type of creating a this is a method of creating a diode. We have the first one, which is the forward bias junction diode. These are the forward bias junction diode looks like. Now let's say we have the PN junction. This is the P, this is the N, this is the holes, and these are the electrons. This is the plus, this is the plus, this is the plus. So now the forward bias should look. So now what happened here, this is the plus, and what happened here is that the N type is connected to the negative part of the negative terminal of the cell battery or whatever you are. This is why the P type is connected to the positive. So this is a forward biased PN junction. So now we also have the reverse biased PN junction. That way the plus or the negative part, the plus is here and the negative part is here. So the N part is connected to the positive and the positive is connected to the negative, and it goes this way. So now the difference between this forward bias and the negative and the reverse bias is that this forward bias has less resistivity, but the reverse bias way of creating this diode has more resistivity. So now we've discussed now on the PN junction diode. Let us now talk on what we call special diodes. There are things we call special diodes. Now this special diode, number one we have is the light emitting diodes. Now these light emitting diodes are produced when elements such as gallium, arsenic, and phosphorus are used in doping. This can be used when they are used in what doping. We represent that one in this manner. The light is emitted. That is how it looks like. Light is emitted there. So now when it is used in doping, when these gases like gallium, arsenic, and phosphorus are used in doping, they emit light. So that's how we have the light emitting diode. And we also have the zener diodes. This zener diode is a special type of diode that is designed for operation of breaking down voltage, or should I say voltage regulation. They either upgrade the voltage or they break down the voltage. And these zener diodes are meant to be used in the breakdown region. The breakdown region of the semiconductor. Breakdown region. So now the most common application of zener diode is voltage regulation. You use it for voltage regulation. You use zener diodes to regulate the voltages in an electronic circuit. So with that being said, we've discussed on diode and diode application. In the next video, we'll be discussing on bipolar junction transistors. Have a wonderful day and anticipate the next video. Bye bye.